Look up on a clear autumn night in the Northern Hemisphere, away from city lights, and you might spot a faint, elongated smudge in the constellation Andromeda. That pale blur appears insignificant to the naked eye, a ghostly wisp barely distinguishable from the darkness around it. But that smudge is actually the Andromeda Galaxy, a colossal island of 1 trillion stars located 2.5 million light-years from Earth. It's the nearest major galaxy to our Milky Way, and it's racing toward us at 250,000 miles per hour. In about 4.5 billion years, these two titans will collide in one of the most spectacular cosmic events imaginable, reshaping both galaxies into something entirely new. For centuries, astronomers mistook Andromeda for a nebula, a cloud of gas within our own galaxy. Only in the 1920s did Edwin Hubble prove it was a separate galaxy, instantly expanding the known universe from one island of stars to billions. That discovery fundamentally changed humanity's place in the cosmos. Today, Andromeda remains one of the most studied objects in the night sky, a laboratory for understanding galactic structure, stellar evolution, dark matter distribution, and the future fate of our own cosmic neighborhood. This journey will take you deep into Andromeda's structure, from its supermassive black hole core to its extended dark matter halo stretching millions of light-years into space. We'll explore its spiral arms, its satellite galaxies, its collision history, and the violent merger awaiting it and the Milky Way. Every chapter reveals new discoveries made possible by decades of observation using radio telescopes, infrared satellites, and the most powerful optical instruments ever built. Andromeda is not just a distant collection of stars, it's a dynamic, evolving system with a complex past and a dramatic future. Let's begin the journey. The historical discovery of Andromeda. The Andromeda Galaxy appeared in written records long before anyone understood what it was. Persian astronomer Abd al-Rahman al-Sufi described it in 964 CE as a small cloud in his Book of Fixed Stars, making it one of the first recorded observations of a deep sky object beyond individual stars visible to the naked eye. For nearly a millennium afterward, observers noted this faint nebulous patch, but lacked the tools to understand its true nature. Early telescopic observations in the 1600s and 1700s revealed more detail, but only deepened the mystery. Was this a cloud of glowing gas within our galaxy, or something else entirely? The breakthrough came in 1923, when Edwin Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory to identify Cepheid variable stars within Andromeda's outer regions. Cepheid variables are giant stars that pulse rhythmically, and their pulsation periods directly correlate with their intrinsic brightness. By measuring how bright these stars appeared compared to how bright they should be intrinsically, Hubble calculated their distance. The result was staggering. Andromeda lay approximately 900,000 light-years away, far beyond the estimated bounds of the Milky Way itself. Hubble's measurement was later refined to 2.5 million light-years, but the implication was immediate and revolutionary. If Andromeda was that distant, it couldn't be a nebula within our galaxy. It had to be a separate galaxy, comparable in size and structure to our own. Overnight, the known universe expanded from one galaxy to countless billions. What had been called spiral nebulae were revealed as distant galaxies, each containing hundreds of billions of stars. The cosmos suddenly became incomprehensibly larger. Andromeda became the nearest major example of these newly recognized galaxies, close enough for detailed study, but far enough to represent the broader population. Astronomers quickly realized it was a spiral galaxy, similar to the Milky Way but somewhat larger. Early photographic plates showed two prominent spiral arms winding outward from a bright central bulge, surrounded by a faint halo of older stars. The spiral structure suggested rotation and active star formation in the arms, while the bulge indicated a dense concentration of ancient stars near the core. Throughout the mid-20th century, astronomers refined distance measurements using improved techniques. Radio astronomy revealed neutral hydrogen gas extending far beyond the visible disk, indicating the galaxy was larger than optical observations alone suggested. Infrared observations in the 1980 and 1990 penetrated dust clouds to map stellar populations hidden from visible light, revealing complex structures in the central bulge and asymmetries in the spiral arms. Space-based telescopes like the Hubble Space Telescope captured unprecedented detail, resolving individual star clusters and nebulae within Andromeda's arms. By the late 20th century, spectroscopic studies measured the galaxy's rotation curve, how fast different regions orbit the center. The results were surprising. Stars in Andromeda's outer regions move faster than expected based on visible matter alone. This discrepancy provided some of the strongest evidence for dark matter, the invisible substance that dominates galactic mass. Andromeda's rotation curve suggested it was embedded in a massive dark matter halo extending hundreds of thousands of light-years beyond the visible stars. Modern measurements using the Hubble Space Telescope and the Gaia spacecraft have precisely determined Andromeda's motion through space. It's approaching the Milky Way at approximately 110 kilometers per second, or about 250,000 miles per hour. This isn't gravitational attraction alone. The two galaxies are on a collision course set billions of years ago. Computer simulations show they will begin merging in roughly 4 to 5 billion years, with the process taking several billion more years to complete. The historical journey from Al-Sufi's small cloud to modern understanding spans over 1,000 years and represents one of astronomy's greatest triumphs. Each technological advance, from early telescopes to photographic plates to radio astronomy to space telescopes, revealed new layers of complexity. What began as a curiosity became the key that unlocked the universe's true scale. Andromeda transformed from a mysterious smudge into a vast galactic system, a cosmic neighbour hurtling toward us through the darkness, and a window into understanding how galaxies form, evolve, and ultimately merge across cosmic time. Today, Andromeda serves as a benchmark for measuring distances to more remote galaxies, a testing ground for theories of galactic structure and dark matter distribution, and a preview of the Milky Way's own future. Its discovery didn't just add one more object to the astronomical catalogue, it fundamentally redefined what the universe is and our place within it. Every observation since has built on Hubble's foundational work, turning that faint smudge into one of the most thoroughly studied objects beyond our own galaxy. The structure and scale of Andromeda. Andromeda dwarfs the Milky Way in almost every measurable dimension. The galaxy spans approximately 220,000 light-years in diameter, making it roughly twice the width of our home galaxy. This enormous disk contains an estimated 1 trillion stars, compared to the Milky Way's 200 to 400 billion. The mass difference is similarly dramatic. Andromeda's total mass, including dark matter, reaches approximately 1.5 trillion solar masses, making it the most massive galaxy in the local group by a significant margin. The galactic disk itself exhibits classic spiral structure, though somewhat less pronounced than idealized spiral galaxies in astronomy textbooks. Two major spiral arms wind outward from the central bulge, traced by bright blue regions of active star formation and glowing hydrogen nebulae. These arms are not solid structures, but density waves, regions where stars, gas, and dust temporarily crowd together as they orbit the center. Material enters the arms, compresses, triggers star formation, then exits as the galaxy's differential rotation carries it forward. Unlike the Milky Way, Andromeda lacks a prominent central bar. The Milky Way's bar structure channels gas inward and helps organize spiral patterns, but Andromeda's central region appears more symmetrical and spherical. This structural difference affects how gas flows through the inner galaxy and where star formation concentrates. Andromeda's spiral arms emanate more directly from the core rather than from the ends of a bar, creating a slightly different pattern than our galaxy's structure. The central bulge contains the galaxy's oldest stellar populations, red and yellow stars, that formed over 10 billion years ago. This region is densely packed, with stars separated by distances far smaller than the average spacing in the galactic disk. The bulge contributes significantly to Andromeda's visible mass and extends several thousand light-years above and below the galactic plane, forming a nearly spherical concentration at the core. Surrounding the disk is the stellar halo, a roughly spherical distribution of old stars and globular clusters, extending more than 100,000 light-years from the center. This halo is sparse compared to the disk stars, are separated by vast distances, sometimes dozens of light-years apart. The halo population is metal poor, meaning these stars contain very few elements heavier than hydrogen and helium, indicating they formed early in the galaxy's history before generations of supernovae enriched the interstellar medium with heavy elements. Andromeda's total luminosity reaches approximately 25 billion times that of the Sun, making it intrinsically brighter than the Milky Way. This higher luminosity comes from both the larger stellar population and a somewhat younger average stellar age in the disk. Star formation in Andromeda continues actively in the spiral arms, producing massive, short-lived blue stars that contribute disproportionately to total light output before exploding as supernovae. The galaxy's rotation presents fascinating complexity. Inner regions orbit faster than outer regions, but the rotation curve flattens at large distances rather than declining, as Newtonian physics would predict for visible matter alone. At about 30,000 light-years from the center, orbital speeds reach approximately 250 kilometers per second and remain roughly constant outward to at least 100,000 light-years. This flat rotation curve is the signature of dark matter dominance in the outer galaxy. Radio observations mapping neutral hydrogen gas reveal that Andromeda's gas disk extends significantly beyond the visible stellar disk. Hydrogen clouds detected at distances exceeding 200,000 light-years from the center show the galaxy's influence reaches much farther than optical telescopes suggest. These outer gas regions rotate more slowly than the stellar disk, but still move too fast to be explained by visible matter, again pointing to dark matter's gravitational effects. The disk itself is not perfectly flat. Infrared observations show subtle warping in the outer regions, where one side of the disk tilts upward relative to the galactic plane, while the opposite side tilts downward. This warp likely results from gravitational interactions with satellite galaxies or from the tidal pull of the Milky Way itself, distorting Andromeda's structure over billions of years. Similar warps appear in many spiral galaxies, including our own, suggesting tidal interactions are common in shaping galactic structure. Andromeda's scale becomes even more impressive when considering its extended dark matter halo. Gravitational modelling suggests this halo reaches at least 600,000 light-years from the centre, possibly extending to 1 million light-years or more. Within this vast volume, dark matter outweighs visible matter by approximately 10 to 1, forming an invisible scaffold that holds the galaxy together and dominates its gravitational field. The halo's exact size and density profile remain active research areas, with different techniques producing somewhat varying results. The galaxy's thickness varies with radius. Near the center, the disk is relatively thick, spanning several thousand light-years vertically. At intermediate distances around 50,000 light-years from the center, the disk thins to roughly 1,000 light-years. In the outermost regions, the disk flares outward again, increasing in thickness as stellar density drops and the transition to the halo becomes gradual rather than sharp. This structure mirrors the Milky Way's own disk geometry, suggesting common formation mechanisms. Comparing Andromeda's scale to familiar distances helps convey its enormity. Light takes 220,000 years to cross from one edge of the visible disk to the other, travelling at 186,000 miles per second every moment of that journey. The distance from Earth to the Sun, 93 million miles, is so small in comparison that light crosses it in just 8 minutes. Andromeda's scale operates on fundamentally different orders of magnitude, where distances are measured in trillions of miles and timescales extend across millions or billions of years. The supermassive black hole at Andromeda's core. At the absolute center of Andromeda lies one of the most extreme objects in the known universe. A supermassive black hole containing approximately 110 to 230 million times the Sun's mass, compressed into a region smaller than our solar system. This black hole, observed indirectly through its gravitational effects on surrounding stars and gas, anchors the entire galaxy and plays a crucial role in regulating star formation in the central regions. Observations from the Hubble Space Telescope resolved the central region with unprecedented detail, revealing that stars within a few light-years of the core orbit at velocities exceeding 1,000 kilometers per second. These extreme speeds can only be explained by an immense concentration of mass in an extraordinarily small volume, precisely what a supermassive black hole produces. By tracking individual stellar orbits over multiple years, astronomers calculated the central mass with increasing precision, confirming the black hole's presence beyond reasonable doubt. Unlike stellar mass black holes formed from collapsing stars, supermassive black holes likely formed through different mechanisms early in galactic history. One theory proposes they grew from smaller seed black holes that merged repeatedly while accreting surrounding gas. Another suggests they formed from the direct collapse of massive gas clouds in the early universe, creating black holes of hundreds of thousands of solar masses immediately. Once formed, these seeds grew over billions of years by consuming gas, stars, and merging with other black holes during galactic collisions. Andromeda's black hole appears relatively quiet compared to active galactic nuclei observed in distant galaxies. It's not currently consuming large amounts of material, so it doesn't produce the brilliant accretion disk and jets characteristic of quasars. Instead, it exists in a quiescent state, occasionally accreting small amounts of gas but generating minimal radiation. This quiescence suggests the central black hole exhausted most available fuel in its immediate vicinity long ago. The black hole's event horizon, the boundary beyond which nothing can escape, has a radius of approximately 680 million kilometers, or about 4.5 times Earth's orbital distance from the Sunday. Within this radius, space-time is so severely curved that all paths lead inward. Time itself slows dramatically near the horizon from an external observer's perspective, approaching infinite dilation exactly at the boundary. Material crossing the event horizon appears to freeze in time from the outside, though from its own reference frame, it crosses unimpeded and reaches the central singularity in finite time. Surrounding the black hole is a dense stellar cluster containing thousands of stars in a region just a few light years across. These stars experience extreme tidal forces from the black hole's gravity forces, strong enough to shred passing stars that venture too close. Such tidal disruption events occur roughly once every 10,000 to 100,000 years in typical galaxies, producing bright flares as stellar material spirals into the black hole and heats to millions of degrees before disappearing beyond the horizon. X-ray observations from satellites like Chandra have detected faint emission from Andromeda's core, indicating some ongoing accretion. The black hole likely captures stellar winds from nearby massive stars and occasionally consumes gas clouds that drift too close. This material forms a temporary accretion disk, heating through friction as it spirals inward. The disk radiates primarily in X-rays and ultraviolet light, though at power levels far below active galactic nuclei. The presence of the supermassive black hole affects star formation throughout the central kiloparsec of the galaxy. Energy released as material falls toward the black hole can heat surrounding gas, preventing it from cooling and collapsing to form new stars. This feedback mechanism helps explain why massive elliptical galaxies and the bulges of large spirals contain predominantly old stars. The central black hole suppresses new star formation by keeping gas too hot to collapse. Andromeda's bulge shows this characteristic, with star formation rates far below those in the spiral arms. Gravitational waves provide another window into black hole physics. Though Andromeda's black hole is too distant and quiescent for current detectors to observe. However, when Andromeda and the Milky Way eventually merge, their central black holes will spiral toward each other over billions of years, eventually merging in a cataclysmic event that will release more energy and gravitational waves than all the stars in both galaxies emit as light. This merger will create a single black hole containing roughly 150 to 280 million solar masses, slightly less than the sum of the two original masses due to energy radiated as gravitational waves. Computer simulations of black hole mergers show the final plunge takes just milliseconds once the black holes approach within a few event horizon radii. The space-time distortions during this merger are so extreme that they produce gravitational waves detectable across hundreds of millions of light years. Future gravitational wave observatories operating in space, such as the planned Laser Interferometer Space Antenna, should detect similar mergers occurring in distant galaxies, providing direct evidence of black hole dynamics that cannot be obtained through electromagnetic observations alone. The black hole's influence extends beyond its immediate vicinity through dynamical friction. As the black hole orbits within the galaxy's potential well, it gravitationally scatters nearby stars, slowly transferring energy and angular momentum. Over billions of years, this process causes the black hole to sink toward the galaxy's center of mass, reaching the location of minimum potential energy. This explains why supermassive black holes consistently reside at galactic centers rather than wandering randomly through the disk. Measurements of Andromeda's black hole mass relative to bulge mass reveal a tight correlation. The black hole contains approximately 0.1 to 0.2% of the bulge's stellar mass. This ratio appears remarkably consistent across different galaxies, suggesting a fundamental connection between black hole growth and galaxy formation. The correlation implies that black holes and their host bulges co-evolve through mutual feedback mechanisms, with each regulating the other's growth over cosmic time. The spiral arms and star formation regions. Andromeda's spiral arms are not static structures frozen in place, but dynamic regions where density waves compress interstellar gas and trigger cascades of new star formation. The galaxy exhibits two major arms winding outward from the central bulge, traced by bright emission from massive young stars and glowing nebulae where hydrogen gas is ionized by intense ultraviolet radiation from these stellar nurseries. The spiral pattern itself results from gravitational instabilities in the rotating disk. As the galaxy spins, regions of slightly higher density exert stronger gravitational pull, attracting more material. This creates self-reinforcing patterns that persist over many rotations, even as individual stars and gas clouds move in and out of the arms. The spiral wave pattern rotates more slowly than the material within the disk, a phenomenon called differential rotation, creating the illusion of stationary spirals while material continuously flows through them. Observations using infrared wavelengths reveal that star formation concentrates along the inner edges of the spiral arms, where gas clouds compress as they enter the density wave. This compression triggers gravitational collapse in molecular clouds, fragmenting them into hundreds or thousands of protostars. The resulting stellar clusters contain stars of all masses, from tiny red dwarfs that will burn for trillions of years to massive blue supergiants that will explode as supernovae within just a few million years. The most massive stars, O and B spectral types, dominate the visible light from spiral arms, despite representing only a tiny fraction of stars by number. These behemoths burn through their nuclear fuel so rapidly that they never drift far from their birthplace before exploding. Their brilliant blue light illuminates the spiral pattern, creating the striking appearance seen in photographs of Andromeda and similar galaxies. The lower mass stars that actually constitute most of the stellar population are too faint to see individually at Andromeda's distance, contributing to a diffuse background glow. Nebulae within the spiral arms provide some of the most visually spectacular features visible from Earth. These glowing clouds of hydrogen gas, heated to thousands of degrees by nearby massive stars, shine with characteristic red light from hydrogen alpha emission. The largest nebulae in Andromeda span hundreds of light years across and contain enough material to form thousands of solar mass stars. Hubble Space Telescope images resolve individual nebulae and star clusters within these regions, revealing details comparable to nebulae in our own galaxy, like the Orion Nebula or the Carina Nebula. The spiral arms also harbour substantial amounts of interstellar dust, microscopic grains of carbon, silicates, and complex molecules formed in the atmospheres of dying stars. This dust obscures visible light from background stars, but emits strongly in infrared wavelengths after absorbing starlight and re-radiating the energy as heat. Infrared observations thus reveal dense concentrations of dust and molecular gas that appear as dark lanes in visible light images. These dark regions represent the raw material for future star formation, not yet collapsed but gradually condensing under gravity. Star formation rates in Andromeda's spiral arms reach approximately 0.5 to 1 solar masses per year, somewhat lower than the Milky Way's estimated 1 to 3 solar masses per year. This difference reflects Andromeda's older average stellar population and somewhat lower gas fraction. Less of its mass remains in the form of unprocessed hydrogen available for new stars. Over cosmic time, galaxies gradually convert gas into stars, reducing star formation rates as available fuel depletes. The spiral structure shows asymmetries suggesting past gravitational interactions. One arm appears slightly more prominent than the other, and both show irregularities in brightness and width along their length. These features likely result from tidal effects during encounters with satellite galaxies, or possibly a distant interaction with the Milky Way itself. Gravitational perturbations from such encounters can amplify spiral patterns temporarily, or create new arm segments that gradually fade over hundreds of millions of years. Dense molecular clouds within the arms regions, where hydrogen molecules dominate over atomic hydrogen, serve as the immediate sites of star formation. These clouds are cold, just 10 to 20 Kelvin above absolute zero, and extremely dense by interstellar standards, containing thousands of molecules per cubic centimeter. When portions of these clouds collapse, they heat through gravitational compression, eventually reaching temperatures and densities where nuclear fusion ignites and a new star is born. Radio telescopes mapping carbon monoxide emission, a tracer for molecular hydrogen, reveal that molecular clouds concentrate in a ring-like structure between about 30,000 and 50,000 light-years from Andromeda's center. This molecular ring coincides with the region of most active star formation, creating a zone where new stellar generations continuously emerge. The ring structure likely reflects the galaxy's rotation pattern, with gas accumulating at radii where orbital dynamics favor cloud formation and persistence. Supernova remnants scattered throughout the spiral arms mark the endpoints of massive stellar evolution. When stars exceeding about 8 solar masses exhaust their nuclear fuel, they collapse and rebound in catastrophic explosions that briefly outshine entire galaxies. These supernovae enrich the interstellar medium with heavy elements forged in stellar cores, and during the explosion itself, carbon, oxygen, iron, and dozens of other elements essential for planets and life. The remnants appear as expanding shells of hot gas, visible in X-ray and radio wavelengths, gradually dispersing their contents into the surrounding medium over tens of thousands of years. Andromeda's satellite galaxy system. Andromeda does not travel through space alone. It commands a retinue of at least 26 confirmed satellite galaxies, with additional candidates awaiting verification. These smaller galaxies orbit Andromeda, much as moons orbit a planet, bound by gravity into long elliptical paths that take hundreds of millions of years to complete. Each satellite represents a smaller galaxy captured by Andromeda's gravity during close encounters, their original independent existence transformed into perpetual orbital motion around the larger system. The two largest and most prominent satellites are M32 and M110, both easily visible through modest amateur telescopes and appearing in photographs as compact elliptical companions flanking Andromeda's disk. M32 sits just 24,000 light-years from Andromeda's center, embedded within the outer spiral structure. This proximity creates intense tidal forces that have stripped away M32's outer regions over billions of years, leaving behind a compact core containing roughly 3 billion stars in a volume spanning just a few thousand light-years across. M32's survival this close to a much larger galaxy testifies to its dense central structure, which resists complete tidal disruption. M110 orbits at a more comfortable distance of about 200,000 light-years from Andromeda's center, maintaining a more intact structure as a result. This dwarf elliptical galaxy contains approximately 10 billion stars and shows evidence of recent star formation unusual for elliptical galaxies, which typically exhausted their gas supplies long ago. Dark lanes of dust visible in high-resolution images suggest M110 captured or retained some gas, triggering localized star formation within the past few 100 million years. Eventually, M110 will spiral closer to Andromeda through dynamical friction, suffering the same fate as M32. Beyond these prominent companions lies a scattered population of much smaller dwarf spheroidal galaxies. These systems contain as few as a few million stars spread across volumes thousands of light-years across, making them so diffuse and faint that discovering them requires careful analysis of stellar surveys. Despite containing relatively few stars, these dwarfs possess disproportionately large amounts of dark matter mass-to-light ratios, reaching 100 times that of the Sun, indicate dark matter dominates their gravitational fields. They represent some of the most dark matter-dominated structures known, with visible stars acting as mere tracers for vast invisible halos. Recent surveys using the Hubble Space Telescope and large ground-based telescopes have discovered satellite galaxies orbiting Andromeda in a flattened, roughly planar distribution rather than spherically distributed as older models predicted. This plane of satellites extends across roughly 400,000 light-years and contains about half of Andromeda's known satellites, all orbiting in roughly the same direction. The existence of such planes challenges some cosmological models that predict satellites should be distributed more randomly in orbits inherited from their dark matter subhalo origins. Several explanations for the satellite plane have been proposed. One suggests the satellites formed from tidal debris during ancient galaxy mergers, naturally placing them in the orbital plane of the original interaction. Another proposes they formed along cosmic filaments, large-scale structures in the dark matter distribution that happen to align with Andromeda's current orientation. A third possibility involves dynamical evolution. Satellites, originally distributed spherically, could migrate toward a planar configuration through gravitational interactions over billions of years. Though simulations suggest this process requires special conditions, the satellite system provides crucial information about Andromeda's total mass and dark matter distribution. By measuring satellite velocities and orbital radii, astronomers can calculate the gravitational force required to keep them bound, revealing the underlying mass distribution. These calculations confirm that Andromeda's mass greatly exceeds its visible stellar mass, with dark matter contributing the dominant share. The satellites effectively act as test particles, probing the galaxy's gravitational potential at various distances. Some satellites show signs of tidal disruption, stretched into elongated streams by Andromeda's gravity. The most dramatic example is the satellite Andromeda 2, which exhibits tidal tails extending tens of thousands of light-years beyond the main body. These tails consist of stars stripped during close approaches to Andromeda, gradually dispersing along the satellite's orbit. Eventually, Andromeda II will be completely torn apart, its stars joining Andromeda's stellar halo as the smaller galaxy's identity disappears entirely. The fate of all satellites ultimately leads to consumption by the central galaxy. Dynamical friction, the gravitational drag exerted by the central galaxy's stars, and dark matter slowly saps orbital energy from the satellites, causing them to spiral inward over billions of years. Smaller satellites merge relatively quickly on cosmic timescales, contributing their stars to the halo. Larger satellites like M32 and M110 will survive longer but eventually succumb to the same process, merging with Andromeda's bulge or disk depending on their orbital characteristics when they finally fall in. Comparing Andromeda's satellite system to the Milky Way's reveals interesting differences. Andromeda appears to have more satellites than the Milky Way, though detection biases make accurate counts. Difficult faint satellites around our own galaxy are harder to detect because we observe them from within the system. The luminosity function of both satellite populations follows similar patterns, suggesting universal processes govern satellite formation and survival around massive galaxies. The satellite galaxies also preserve fossil records of early galactic assembly. Their old stellar populations, low metallicity, and lack of recent star formation indicate they formed early in cosmic history, possibly within the first billion years after the Big Bang. Studying their chemical composition and stellar ages provides insights into conditions during the epoch of galaxy formation, complementing observations of distant, high-redshift galaxies that show the universe in its youth directly. The collision history of Andromeda. Andromeda's current structure bears the scars of multiple past collisions, each leaving distinctive signatures in its stellar populations, kinematics, and large-scale structure. Galaxies in the universe do not evolve in isolation, they grow through mergers, consuming smaller neighbours and occasionally colliding with comparably sized systems. Andromeda's history includes at least 2 major mergers and numerous minor ones, all contributing to its present form. Spectroscopic surveys of individual stars in Andromeda's halo reveal multiple distinct populations with different chemical compositions and orbital characteristics. These populations cannot have formed together, they represent remnants of separate galaxies that merged with Andromeda at different times in the past. By analysing their orbits and chemical abundances, astronomers can reconstruct the merger history, identifying when each collision occurred and estimating the mass of the consumed galaxy. The most recent major merger likely occurred approximately 1.8 to 3 billion years ago, when a galaxy containing several billion stars collided with Andromeda. This event disrupted the pre-existing disk structure, heating stellar orbits and puffing up the disk thickness. Computer simulations show that such mergers scatter stars from the disk into the halo, explaining the extended stellar halo observed today. The merger also triggered bursts of star formation as gas clouds collided and compressed, creating new stellar populations whose ages correspond to the timing of the collision. Evidence for this recent merger appears in the galaxy's kinematics. Stars in certain regions of Andromeda's halo move in coordinated streams rather than random orbits, indicating they originated from the same progenitor galaxy and retain memory of their original orbital motion. These stellar streams wrap around Andromeda in long arcs, some extending hundreds of thousands of light-years, the tidal remnants of a galaxy gradually torn apart by Andromeda's gravity during the merger process. An earlier major merger occurred roughly 8 to 10 billion years ago, involving an even larger galaxy, possibly 20% of Andromeda's mass at that time. This ancient collision profoundly affected Andromeda's structure, contributing significantly to its thick disk and stellar halo. The collision likely destroyed any pre-existing thin disk, mixing stellar populations and erasing previous spiral patterns. The galaxy spent billions of years reforming its disk structure from gas that settled back into rotation after the merger's chaotic disruption. The thick disk itself, a component of stars orbiting in a puffed-up layer above and below the thin disk, likely formed primarily from these major mergers. Thick disks are common in large spiral galaxies and universally show older stellar populations and higher vertical scale heights compared to thin disks. Their formation mechanism involves heating of pre-existing disk stars during mergers, scattering them into higher inclination orbits. Andromeda's thick disk extends several thousand light-years above and below the plane, containing stars averaging 8 to 10 billion years old. Beyond these major events, Andromeda continuously accretes smaller dwarf galaxies. Each minor merger adds stars to the halo and may perturb the disk structure slightly, but lacks the mass to cause dramatic disruption. These ongoing minor mergers occur every few 100 million years on average, gradually building the halo and contributing to the complex stellar stream network visible in deep photographic surveys. Some current satellites like M32 will eventually merge, becoming future additions to this accretion history. The merger history connects to Andromeda's current star formation rate and gas content. Major mergers drive gas toward galactic centers through gravitational torques, fueling intense starbursts that can temporarily increase star formation rates by factors of 10 or more. The merger 2 billion years ago likely triggered such a starburst, explaining the presence of intermediate-age stellar populations in Andromeda's bulge stars, too young to have formed in the galaxy's earliest epochs, but older than recent disk star formation. These populations provide a fossil record of merger-driven star formation. The giant stellar stream discovered wrapping around Andromeda's outer regions represents the most visible merger remnant. This stream contains stars distributed in a thin arc spanning over 100,000 light-years, with kinematics indicating it originated from a dwarf galaxy that passed close to Andromeda roughly 2 billion years ago. The encounter stripped stars from the dwarf's outer regions, depositing them in a trail marking its orbital path. The progenitor galaxy itself may still exist as one of Andromeda's current satellites, stripped down to a dense core that survived the close passage. Chemical abundance patterns in merger remnants reveal details about the progenitor galaxies. Stars with lower metallicity, fewer heavy elements, indicate formation in smaller galaxies, where supernova enrichment proceeded more slowly. By mapping metallicity across Andromeda's halo, astronomers identify regions dominated by different merger remnants, each with characteristic metallicity reflecting its progenitor's mass and star formation history. This chemical archaeology allows reconstruction of merger events that occurred billions of years ago, long before Earth formed. The collision history also shaped Andromeda's dark matter distribution. Simulations show that mergers can transfer dark matter from infalling satellites to the main halo, increasing central dark matter density. However, gravitational scattering from baryonic matter during mergers can also decrease central dark matter density, a process called dark matter heating. The resulting dark matter profile depends on the detailed merger history, making Andromeda's observed dark matter distribution a test of galaxy formation models. Future mergers are already predetermined by current orbital motions. Several of Andromeda's satellites orbit on collision courses that will result in mergers within the next few billion years. M32's close proximity suggests it will merge relatively soon on cosmic timescales, possibly within 2 to 3 billion years. M110's wider orbit gives it more time, but eventual merger remains inevitable. These future events will slightly increase Andromeda's mass and add stars to its halo, continuing the growth process that has operated throughout cosmic history. The ultimate merger awaits in approximately 4.5 billion years when Andromeda and the Milky Way collide. This will be Andromeda's largest merger since its formation, involving two galaxies of comparable mass. The event will transform both systems, creating a giant elliptical galaxy and fundamentally altering the structure built over billions of years. This future collision represents the culmination of Andromeda's merger history, the final major event that will define its ultimate form. The dark matter halo of Andromeda, surrounding Andromeda's visible stars and gas, extends an enormous, invisible structure containing more mass than everything we can see, the dark matter halo. This ghostly component dominates the galaxy's gravitational field, extending at least 600,000 light-years from the center and possibly reaching 1 million light-years or more. Dark matter comprises roughly 90% of Andromeda's total mass, forming an invisible scaffold that holds the galaxy together and governs the motion of every star, gas, cloud, and satellite within its domain. Evidence for dark matter's existence comes primarily from measuring how fast objects orbit at various distances from Andromeda's center. According to Newtonian physics, orbital velocity should decrease with distant objects farther from the mass. Concentration should move more slowly, just as outer planets in our solar system orbit more slowly than inner planets. However, observations show that Andromeda's rotation curve remains flat far beyond the visible disk. Stars at 100,000 light-years from the center orbit at roughly the same speed as stars at 30,000 light-years, approximately 250 kilometers per second. This flat rotation curve can only be explained by invoking additional mass distributed throughout a large halo. The visible stars and gas account for perhaps 10% of the mass required to produce the observed velocities. The remaining 90% must be some form of matter that exerts gravity but doesn't emit, absorb, or scatter light at any wavelength, hence the name dark matter. Without this unseen component, Andromeda's outer stars would fly off into intergalactic space, unable to maintain stable orbits. The dark matter halo's density decreases smoothly with distance from the center, following a profile described by mathematical functions like the NFW, Navarro-Frank-White profile, derived from cosmological simulations of structure formation. Near the center, dark matter density reaches hundreds of times the cosmic average. At distances of several 100,000 light-years, density drops to just a few times average. This radial profile emerged naturally from the collapse and merger of dark matter clumps during Andromeda's formation billions of years ago. Computer simulations of galaxy formation always produce dark matter halos with these general characteristics, regardless of the specific details of star formation and gas physics. This universality suggests dark matter halos form first through purely gravitational processes operating on primordial dark matter density fluctuations from the early universe. Ordinary matter later falls into these pre-existing gravitational wells, cooling and condensing to form stars and galaxies. In this picture, galaxies like Andromeda are essentially the visible tips of far larger dark matter structures. The halo's mass can be estimated through several independent methods. Measuring satellite galaxy orbits provides one technique. Satellites respond only to total gravitational force, allowing calculation of total enclosed mass at their orbital radii. Studies of satellite motions indicate Andromeda's halo contains approximately 1 to 1.5 trillion solar masses within 600,000 light-years. Another method uses gravitational lensing, where Andromeda's gravity bends light from more distant background galaxies. The amount of lensing depends on total mass along the line of sight, providing another mass estimate consistent with satellite measurements. The composition of dark matter remains one of physics' greatest unsolved mysteries. Particle physics proposes several candidates. Most prominently, WIMPs, weakly interacting massive particles. Hypothetical particles with mass roughly 10 to 1,000 times a proton, but interacting only through gravity and the weak nuclear force. Despite decades of underground detector experiments designed to catch rare interactions between WIMPs and ordinary matter, no confirmed detection has been made. Alternative candidates include axions, extremely light particles, sterile neutrinos, or primordial black holes formed in the early universe. Regardless of composition, dark matter particles would be swarming through Andromeda's volume, passing through ordinary matter without interacting. In regions where dark matter density is high, like near galactic centers, these particles orbit rapidly, creating a dynamic dark matter atmosphere. Near Earth's location in the Milky Way, dark matter density is estimated at roughly 0.3 GeV per cubic centimeter, equivalent to about 1 proton mass per cubic centimeter, extraordinarily diffuse by terrestrial standards, but significant when integrated over galactic volumes. The dark matter halo plays a crucial role in galaxy evolution beyond simply holding the system together gravitationally. During galaxy mergers, dark matter halos merge first, with the visible galaxies embedded following later. The halo merger generates gravitational tides and shock heating that affect gas dynamics and star formation in the visible components. Computer simulations show that merger outcomes depend strongly on the structure and concentration of the dark matter halos involved. Concentrated halos produce different results than diffuse ones. Observations of Andromeda's halo shape suggest it may be slightly flattened rather than perfectly spherical, possibly aligned with the galactic disk. This flattening could result from the galaxy's formation history if Andromeda formed through anisotropic accretion, with more material falling in along certain directions. The halo would naturally develop some asymmetry. Alternatively, the disk's gravity might gravitationally pull on dark matter particles, creating a slight flattening over billions of years. Current observations cannot definitively distinguish between these possibilities due to uncertainties in measuring halo properties at large radii. The dark matter distribution near Andromeda's center, within a few thousand light-years, remains particularly uncertain. Some theoretical models predict density should increase steeply toward a central cusp, while others suggest interactions between dark matter and baryonic matter during galaxy formation might create a constant density core. Observations of stellar kinematics near the center could potentially distinguish these scenarios, but disentangling dark matter effects from those of the central supermassive black hole and dense stellar bulge proves extremely challenging. Substructure within the dark matter halo adds another layer of complexity. Cosmological simulations predict thousands of dark matter subhalos, smaller clumps that survived tidal disruption during their infall into the main halo. Most subhalos lack visible galaxies because they're too small to have retained gas for star formation, but their gravitational effects might be detectable through careful analysis of stellar streams. If a dark matter subhalo passes near a stellar stream, its gravity creates a gap or kink in the stream's otherwise smooth distribution. Detecting such features would provide rare, direct evidence of dark matter structure beyond its smooth component. The dark matter halo extends so far that Andromeda's halo and the Milky Way's halo may already overlap in the space between them. Dark matter particles from each galaxy's outskirts currently intermingle, though at densities too low to produce observable effects. As the galaxies approach over the next few billion years, their halos will interpenetrate more deeply, exchanging angular momentum and energy. This halo merger will actually precede the collision of visible components by hundreds of millions of years, setting the stage for the eventual stellar merger. Understanding dark matter's properties remains essential for comprehending Andromeda's formation, current structure, and future evolution. Every aspect of the galaxy's behavior, from satellite orbits to disk stability to merger dynamics, depends critically on dark matter's distribution and density. Andromeda serves as a natural laboratory for dark matter research, allowing astronomers to test theoretical predictions against observations of a real galaxy similar to, but external to our own. Advances in dark matter physics will inevitably deepen our understanding of Andromeda, while detailed observations of Andromeda provide crucial constraints on dark matter theories. The stellar populations of Andromeda. Andromeda contains not one uniform population of stars, but multiple distinct populations, each telling part of the galaxy's formation and evolution story. These populations differ in age, chemical composition, spatial distribution, and kinematics, reflecting the complex history of star formation and galaxy assembly over cosmic time. By analysing stellar populations, astronomers reconstruct how Andromeda transformed from a collection of primordial gas clouds into the massive spiral galaxy observed today. The oldest stellar population resides primarily in the halo and bulge, containing stars formed 10 to 13 billion years ago during Andromeda's earliest epochs. These ancient stars are metal poor, with iron abundances often just 1% of the solar value, indicating formation before generations of supernovae enriched the interstellar medium with heavy elements. Their colours appear distinctly redder than younger populations, dominated by low-mass stars that have spent billions of years slowly burning hydrogen into helium. The most massive stars from this generation exploded as supernovae long ago, leaving only their smaller, longer-lived companions. Chemical analysis of halo stars reveals diverse abundance patterns, suggesting they formed in multiple smaller galaxies that later merged with Andromeda. Some halo stars show abundance ratios characteristic of dwarf galaxy chemical evolution, where supernova enrichment proceeded differently than in larger systems. These fossil records, encoded in stellar chemistry, allow astronomers to identify merger remnants and estimate the masses and star formation histories of the progenitor galaxies. Each merger added its stellar population to Andromeda's halo, creating the complex mixture observed today. The thick disk population represents stars formed 8 to 10 billion years ago, after Andromeda's major merger phase, but before the current thin disk assembled. These stars orbit in a flattened distribution, but with significant vertical motion, creating a disk roughly 3,000 light-years thick. Their metallicities are intermediate, higher than halo stars, but lower than thin disk stars, reflecting formation from gas partially enriched by earlier stellar generations. Thick disk stars likely formed during or shortly after major mergers, when gas settling back into rotation produced a burst of star formation throughout a vertically extended region. The thin disk contains Andromeda's youngest stellar populations, with ages ranging from newly formed stars still embedded in nebulae to stars several billion years old. This population exhibits the highest metallicities, some stars containing twice the solar abundance of iron and other heavy elements. The thin disk's scale height is just 1,000 light-years near the Sun's equivalent radius, creating the flat structure visible in edge-on images. Star formation continues actively in the thin disk's spiral arms, adding new generations that will gradually enrich the interstellar medium further as massive stars explode. Stellar age gradients exist throughout Andromeda's disk. Inner regions contain older average stellar ages than outer regions. This inside-out formation pattern appears universal among disk galaxies and reflects how gas settles during galaxy assembly. Dense central regions formed stars efficiently early on, quickly converting available gas into stars. Outer regions received gas more gradually, sustaining lower star formation rates over longer periods. This pattern explains why galaxy centers appear redder than outer disks. Red color indicates older, cooler stars dominating the population. Main sequence stars, those actively burning hydrogen in their cores, constitute the majority by number, but contribute relatively little to total luminosity. These range from massive O and B stars with surface temperatures exceeding 30,000 Kelvin and lifetimes measured in millions of years, to tiny M dwarfs, cooler than 3,500 Kelvin that will burn for trillions of years. The Sun represents a middle-aged G-type star, neither particularly massive nor faint. In Andromeda, most stars fall toward the lower mass end. Red dwarfs outnumber solar-type stars by roughly 10 to 1, and outnumber massive stars by factors exceeding 1,000 to 1. Giant stars represent later evolutionary stages, when stars exhaust core hydrogen and expand dramatically. Red giants swell to sizes hundreds of times larger than main sequence stars, their surfaces cooling to temperatures around 3,000 to 4,000 Kelvin. These giants contribute disproportionately to galaxy luminosity despite representing just a few % of stars by number. Andromeda's bulge appears particularly bright, partly because its old population has had billions of years for lower mass stars to evolve into the giant phase. Horizontal branch and red clump stars populate a specific region in color magnitude diagrams, representing helium-burning phases in stellar evolution. These phases last much shorter than main sequence phases, just 100 million years, compared to billions for the main sequence, but produce distinct observational signatures. By counting horizontal branch stars and comparing to stellar evolution models, astronomers estimate average ages of stellar populations. Andromeda's halo horizontal branch extends to very blue colors, indicating predominantly old, metal-poor populations exceeding 10 billion years age. Variable stars provide additional information about stellar populations. Cepheid variables, pulsating yellow giants, whose periods relate to intrinsic brightness, serve as distance indicators and age tracers. Longer period Cepheids are younger and more massive, while shorter period Cepheids are older. RR Lyrae variables, another class of pulsating stars, appear in old populations and inhabit Andromeda's halo in substantial numbers. Observing these variables requires repeated imaging to detect brightness changes, but the effort yields precise ages and distances. White dwarfs represent stellar end states. For stars below about 8 solar masses, the burned-out cores, left after giant stars, shed their outer envelopes. These dense remnants pack roughly half the Sun's mass into Earth-sized volumes, supported against gravitational collapse by electron degeneracy pressure. Andromeda contains billions of white dwarfs, though their faintness makes individual detection difficult except for the nearest and brightest examples. The white dwarf population grows continuously as intermediate mass stars complete their evolution, gradually shifting more mass from active stars to inert remnants. Neutron stars and black holes, remnants of massive star supernovae, also populate Andromeda, though their numbers are much smaller than white dwarfs. Neutron stars pack 1.4 to 2 solar masses into spheres just 20 kilometers across, creating densities exceeding atomic nuclei. Stellar mass black holes form from the most massive progenitors, containing 5 to 50 solar masses compressed into volumes smaller than cities. Most remain dark and invisible, detectable only when they capture gas from companion stars or through gravitational effects on nearby objects. Studying Andromeda's stellar populations requires sophisticated techniques combining photometry, spectroscopy, and theoretical modeling. Color magnitude diagrams plotting stellar brightness versus color reveal distinct population sequences corresponding to different evolutionary phases and ages. Spectroscopic observations measure chemical abundances and radial velocities, providing three-dimensional information about stellar motions and compositions. Comparing observations to stellar evolution models yields ages, masses, and evolutionary states for individual stars and populations. The stellar populations reveal that Andromeda formed through hierarchical assembly. Smaller systems merged to build increasingly larger structures, with star formation occurring throughout this process. The diverse populations represent snapshots from different epochs, preserved like geological strata in rock formations. By reading these stellar fossil records, astronomers reconstruct Andromeda's biography from birth to present, revealing a complex history of gas accretion, merger events, and continuous star formation extending across cosmic time. The interstellar medium and gas dynamics. Between Andromeda's stars lies a vast ocean of gas and dust in the interstellar medium, comprising roughly 10% of the galaxy's baryonic mass and serving as raw material for future star formation. This medium exists in multiple phases, ranging from cold molecular clouds at 10 Kelvin to million-degree plasma heated by supernova shocks, each phase playing distinct roles in the galaxy's ecology. Understanding gas dynamics reveals how Andromeda converts pristine hydrogen into stars, and how stellar processes return enriched material to interstellar space. Neutral atomic hydrogen dominates by mass, distributed throughout a disk, extending significantly beyond the stellar disk to radii exceeding 200,000 light-years. Radio telescopes mapping the 21-centimeter emission line from neutral hydrogen reveal detailed structure, including spiral arm concentrations, gaps, and a warped outer disk. Total neutral hydrogen mass reaches approximately 4 billion solar masses, providing substantial fuel for star formation over the next several billion years at current rates. The hydrogen distribution shows clear spiral patterns aligned with the stellar arms but extending outward into regions lacking significant stellar populations. Gas enters spiral density waves from interarm regions, compresses, and triggers star formation before exiting the arms and expanding again. This process creates the characteristic pattern of young stars tracing spiral arms they form within the compressed gas, but haven't drifted far before their brilliant blue light marks the arm's location. Molecular hydrogen, H2 molecules, rather than individual atoms, exists in the coldest, densest regions where gas self-shields from dissociating ultraviolet radiation. These molecular clouds typically contain 100 to 10,000 solar masses, concentrated in volumes just tens of light-years across, with internal temperatures around 10 to 20 Kelvin. Carbon monoxide emission serves as a proxy for molecular hydrogen, which lacks a strong radio emission line. CO mapping reveals molecular clouds concentrated in a ring between 30,000 and 50,000 light-years from Andromeda's center, coinciding with peak star formation activity. The molecular gas mass totals approximately 400 million to 1 billion solar masses, an order of magnitude less than neutral hydrogen, but far more immediately relevant to star formation. Stars form exclusively in molecular clouds where densities reach levels allowing gravitational collapse. The molecular to atomic ratio varies with galactic radius higher near the center, where dust shielding is more effective, lower in the outer disk, where ultraviolet radiation more easily dissociates molecules. Ionized hydrogen creates the visually spectacular emission nebulae visible in high-resolution images. Massive O and B stars emit copious ultraviolet photons that ionize surrounding hydrogen, creating HII regions, bubbles of 10,000 Kelvin plasma, extending tens to hundreds of light-years across. These nebulae shine with characteristic red light from hydrogen alpha emission, allowing easy identification even at Andromeda's distance. The largest HII regions contain enough gas to form thousands of solar mass stars, representing some of the galaxy's most active star-forming sites. Supernova remnants inject huge quantities of energy into the interstellar medium, creating expanding shells of million-degree plasma detectable in X-rays. A typical supernova releases 10 51 ergs, enough energy to power the Sun's output for 10 billion years instantaneously into surrounding gas. This energy drives shock waves that sweep up and compress ambient gas, triggering secondary star formation while simultaneously heating and disrupting nearby clouds. Supernova-driven turbulence regulates star formation efficiency, preventing gas from collapsing too rapidly and allowing galaxies to sustain star formation over billions of years. Dust grains, though comprising less than 1% of gas mass, profoundly affect observational appearance and chemical processes. These microscopic particles of carbon and silicates form in the atmospheres of cool giant stars and in supernova ejecta, gradually accumulating in interstellar space. Dust absorbs ultraviolet and visible light, heating to approximately 20 to 50 Kelvin and re-radiating in infrared wavelengths. This process creates the dark lanes visible in optical images and the bright infrared emission revealing dust-obscured star formation regions. Gas dynamics in Andromeda's disk exhibit complex patterns beyond simple circular rotation. Observations reveal non-circular motions, indicating gas flows toward or away from the spiral arms, radial streaming motions, and vertical oscillations above and below the midplane. These motions reflect gravitational perturbations from spiral density waves, stellar bars, though Andromeda lacks a prominent bar, and past merger events. Understanding these flows requires sophisticated modeling, combining observational constraints with hydrodynamic simulations. The outer gas disk shows pronounced warping similar to that in the stellar disk, with one side elevated and the opposite side depressed relative to the inner disk plane. This warp likely results from gravitational interactions with satellite galaxies, particularly M31 and M110, whose tidal forces during close passages torque the outer disk. Gas in the warp experiences different gravitational forces than inner regions, altering its rotational dynamics and potentially affecting star formation efficiency in these regions. Gas accretion from intergalactic space may supplement Andromeda's gas supply, though observational evidence remains indirect. Theoretical models suggest massive galaxies continuously accrete low metallicity gas from the cosmic web, long filaments of matter connecting galaxies and galaxy clusters. This cold mode accretion would flow along filaments directly into galaxy disks, providing fresh hydrogen to sustain star formation. Detection requires sensitive observations of faint emission from warm diffuse gas surrounding galaxies, a challenging observation that has produced tentative results. Gas outflows driven by stellar winds and supernovae create large-scale structures extending above and below the disk. When numerous supernovae explode in close spatial and temporal proximity, common in regions of intense star formation, their combined energy creates superbubbles that can break through the disk into the halo. These chimneys allow hot gas to escape into intergalactic space, potentially carrying metals produced by stellar nucleosynthesis far from their formation sites. The Fermi bubbles discovered around the Milky Way suggest similar structures might exist around Andromeda, though they would be challenging to detect at its distance. The interstellar medium serves as both the source and repository of stellar material in a continuous cycle. Stars form from cold molecular gas, spend their lives fusing hydrogen into heavier elements, and return enriched material to the medium through stellar winds and supernovae. This galactic ecology gradually increases metallicity over time, evidenced by the higher metal content in young stars compared to old. Understanding this cycle requires tracking gas from diffuse atomic phase through molecular cloud formation, star formation, stellar evolution, and finally back to diffuse gas, enriched with new elements. Magnetic fields thread through the interstellar medium, typically aligned with spiral arms and reaching strengths of several microgauss, millions of times weaker than Earth's surface field, but significant over interstellar distances. These fields affect gas dynamics by providing additional pressure support against gravitational collapse and by guiding the motion of charged particles. Synchrotron emission from electrons spiraling through magnetic fields provides one method to map field structure, revealing that Andromeda's field follows a spiral pattern similar to stellar and gas spirals. Chemical composition varies throughout the interstellar medium based on local star formation history and mixing processes. Regions near star-forming complexes show enhanced abundances of elements like oxygen, carbon, and nitrogen produced by recent supernovae, while regions far from star formation sites retain lower metallicities closer to primordial values. Measuring these abundance gradients requires spectroscopy of emission nebulae or individual stars, techniques that have revealed radial metallicity gradients decreasing from center to outer disk, a pattern consistent with inside-out galaxy formation. Andromeda's star formation history. Andromeda did not form all its stars at once, but accumulated them gradually through a complex star formation history, spanning the universe's entire history since 13.8 billion years ago. This history, reconstructed from stellar population studies and chemical abundance patterns, reveals periods of intense starburst activity alternating with quieter phases of steady star formation, each episode leaving distinctive signatures in the present-day galaxy. The earliest stars formed within the first billion years after the Big Bang, during the epoch when the universe's first galaxies assembled from primordial gas clouds. These population 3 stars, containing virtually no elements heavier than helium, were massive and short-lived, exploding as supernovae that enriched their surroundings with the first heavy elements. Andromeda's oldest surviving stars, found primarily in the halo, date to this era, though the true population 3 stars themselves have long since died, their legacy preserved only in the slight metal enhancement they imprinted on subsequent generations. Major merger events punctuated the early history with intense starbursts. Computer simulations indicate Andromeda experienced significant mergers approximately 8 to 10 billion years ago, and again 2 to 3 billion years ago. These collisions funneled vast quantities of gas toward the central regions through gravitational torques, triggering star formation rates potentially exceeding 10 solar masses per year, several times higher than current rates. The resulting stellar populations, now aged and redder, contribute to Andromeda's prominent bulge and thick disk. Between major mergers, star formation continued at lower but sustained rates as gas gradually settled into the rotating disk. This secular evolution phase allowed the thin disk to build up slowly, forming stars from gas that cooled and condensed without violent disruption from mergers. The thin disk's intermediate age population, roughly 2 to 8 billion years old, likely formed during this quieter period. Spiral structure became established as the disk gained enough mass and rotational support to develop gravitational instabilities that seed spiral density waves. Star formation rates peaked around 8 to 10 billion years ago, when Andromeda contained more abundant gas and experienced frequent mergers. Estimates suggest rates possibly reached 5 to 10 solar masses per year during this period, compared to the current 0.5 to 1 solar masses per year. This decline reflects both gas consumption into stars and gradual reduction of gas accretion from the intergalactic medium as the universe aged and cosmic expansion accelerated. Recent star formation concentrates in spiral arms where gas compression triggers cloud collapse. Observations resolve individual star-forming regions, revealing that star formation proceeds in clusters rather than uniformly distributed. Giant molecular clouds fragment into hundreds of protostars over timescales of a few million years, creating clusters containing stars of all masses from the initial mass function statistical distribution. These clusters gradually disperse as stellar winds and supernova explosions from massive members disrupt the remaining gas. The current star formation rate of approximately 0.5 to 1 solar masses per year, though seemingly small, will produce tens of billions of new stars over the next several billion years if maintained. However, rates will likely decline further as available gas depletes through continued star formation and possible ejection through galactic winds. Eventually, Andromeda will exhaust its gas supply, star formation will cease, and the galaxy will transition to a red and dead state dominated by old, cool stars. Chemical evolution closely parallels star formation history. Metallicity, the abundance of elements heavier than helium, increases monotonically as successive stellar generations cycle material through nuclear fusion and explosion. Andromeda's metallicity gradient shows the highest values near the center, where star formation occurred earliest and most intensely, gradually decreasing to lower values in outer regions that formed later. This gradient quantifies the inside-out formation scenario, with inner regions reaching solar metallicity or higher, while outer regions remain metal poor. Specific element ratios provide additional chronological information. Alpha elements, like oxygen, magnesium, and silicon, are produced by short-lived massive stars, while iron comes primarily from longer-lived Type Ia supernovae that explode billions of years after formation. The alpha to iron ratio thus indicates formation timescales. High ratios suggest rapid star formation that ended before Type Ia supernovae contributed significantly, while lower ratios indicate extended star formation, allowing iron enrichment to catch up. Stellar age dating employs multiple techniques. Main sequence turn-off points, the luminosity at which stars are just exhausting core hydrogen, shift to lower luminosities in older populations, since lower mass stars have longer main sequence lifetimes. Comparing observed turn-off points to stellar evolution models yields population ages. White dwarf cooling ages provide another chronometer. Older populations contain cooler, fainter white dwarfs that have spent more time cooling. Radioactive dating of long-lived isotopes in meteorites, though limited to solar neighborhoods, calibrates stellar evolution models against absolute ages. Star formation efficiency, the fraction of gas converted into stars per unit time, varies spatially within Andromeda. Central regions exhibit higher efficiency due to greater gas densities and more frequent cloud collisions, while outer regions form stars less efficiently from more diffuse gas. This efficiency variation creates radial gradients in gas depletion times. Inner regions will exhaust their gas supplies within a few billion years at current rates, while outer regions possess fuel for tens of billions of years of continued low-level formation. Environmental effects influence star formation on local scales. HII regions, ionized bubbles around massive stars, compress surrounding neutral gas at their expanding edges, potentially triggering new star formation in a positive feedback process. Conversely, supernova explosions disrupt nearby molecular clouds, temporarily suppressing formation. These competing processes regulate formation rates, preventing either runaway star formation that would consume gas catastrophically quickly or complete quenching that would halt formation entirely. Comparing Andromeda's star formation history to the Milky Way reveals interesting differences despite similar present structures. Andromeda appears to have undergone its most intense formation period slightly earlier and experienced a more recent significant merger, explaining its somewhat larger size and mass. The Milky Way shows evidence of ongoing minor mergers with dwarf satellites that contribute fresh gas, while Andromeda's star formation appears declining more steadily without recent gas-rich accretion events. Future star formation in Andromeda faces certain termination when the Milky Way collision occurs in 4 to 5 billion years. The merger will trigger an intense starburst as gas clouds from both galaxies collide at relative velocities of hundreds of kilometers per second, compressing them to star-forming densities. This final burst may produce 10 to 100 solar masses per year, briefly, forming perhaps 10 to 100 billion new stars before exhausting accessible gas. Afterward, the merged galaxy will fade into a quiescent elliptical system, its star formation history concluded. The approaching collision with the Milky Way. Andromeda and the Milky Way are on an inevitable collision course that will culminate in approximately 4.5 billion years, fundamentally transforming both galaxies. This is not speculation. Precise measurements using the Hubble Space Telescope have tracked Andromeda's motion across the sky over decades, revealing a tangential velocity nearly perpendicular to the line of sight, combined with a radial approach velocity of 110 kilometers per second. These measurements confirm the galaxies will merge rather than pass by, creating one of the most significant cosmic events in our local universe's future. The collision actually began, in a sense, millions of years ago, as the galaxy's extended dark matter halos already overlap in the space between them. Dark matter particles from each galaxy's outskirts currently intermingle, though at densities too low to produce observable effects. This halo interaction will intensify over the next few billion years, with tidal forces gradually distorting both galaxies' outer structures long before the visible components collide. Current projections suggest the first close passage will occur in approximately 4 billion years. At this point, the galaxies will pass through or very near each other, their disks potentially interpenetrating depending on the precise orientation at closest approach. The encounter will unleash enormous tidal forces that stretch and distort both galaxies, flinging long streams of stars into intergalactic space in graceful arcs, marking the interaction's violence. These tidal tails, similar to those observed in colliding galaxies throughout the universe, will extend hundreds of thousands of light years, temporarily dwarfing both progenitor galaxies. Despite containing a combined 2 trillion stars, the probability of direct stellar collisions remains negligible. Stars are separated by distances millions of times their diameters. Even when galaxies interpenetrate, stars pass between each other like 2 swarms of gnats passing through each other. Individual stars will receive gravitational perturbations altering their orbits, but physical impacts between stars are essentially impossible. The drama plays out in gas clouds and large-scale gravitational dynamics rather than stellar collisions. Gas clouds will collide spectacularly. Unlike stars, interstellar gas occupies substantial volumes and will impact at relative velocities approaching 200 to 300 kilometers per second. These collisions compress gas to densities where gravitational collapse becomes inevitable, triggering the most intense starburst the local group has experienced in billions of years. Formation rates could temporarily exceed 100 solar masses per year, illuminating both galaxies with brilliant blue light from millions of newly formed massive stars. After the first passage, the galaxies will separate again, gravity insufficient to capture them in a single encounter. They'll swing apart over the next billion years, their mutual gravity slowly converting their kinetic energy into potential energy until reaching maximum separation, perhaps 500,000 light-years or more. Then gravity will pull them together again for a second collision roughly 6 billion years from now, this time with less kinetic energy remaining for another escape. Multiple passages over several billion years will gradually merge the systems into a single structure. Computer simulations of the merger show the eventual outcome: a giant elliptical galaxy informally named Milkomeda or Milkdromeda. The graceful spiral structure of both progenitors will be completely destroyed. Stars scattered into randomly oriented orbits, creating the featureless, smooth, elliptical appearance characteristic of merger remnants. The combined system will contain roughly 1 trillion stars, spanning approximately 150,000 to 200,000 light-years, smaller than the original galaxy's combined extent due to gravitational settling, and energy dissipation through tidal heating. The central supermassive black holes, 4 million solar masses from the Milky Way and 110 to 230 million from Andromeda, will spiral toward each other through a process called dynamical friction. As each black hole moves through the merged galaxy's stellar population, gravitational encounters with stars gradually sap orbital energy, causing the black holes to sink toward the combined center of mass. This process requires hundreds of millions of years, eventually bringing the black holes within light years of each other. At close separations, gravitational wave emission becomes the dominant mechanism removing orbital energy. The black holes will spiral together with increasing speed, eventually merging in a fraction of a second in a cataclysmic event that releases more energy in gravitational waves than all the stars in the merged galaxy emit as light. The resulting black hole will contain approximately 150 to 280 million solar masses, slightly less than the sum of progenitors, because a few percent of mass converts to gravitational wave energy radiating into space. Earth's fate during this collision depends on countless unpredictable details. The Sun and its planets might be flung into the halo by gravitational encounters, ejected into intergalactic space, or dropped into closer orbits around the merged galaxy's center. Statistically, ejection into the halo or beyond seems most likely given the chaotic dynamics during merger. However, Earth faces a more imminent threat. In approximately 5 billion years, the Sun will exhaust core hydrogen and expand into a red giant, likely engulfing Earth long before the galactic merger completes. Any civilization surviving in the merged galaxy will observe a dramatically different night sky. Instead of two distinct spiral galaxies, observers will see a smooth distribution of stars in all directions, much denser than current views from Earth. The nearest stars will likely be closer than current solar neighborhood distances, increasing the probability of gravitational perturbations affecting planetary systems. However, the galaxy will be quieter star formation, largely exhausted, fewer supernovae, less turbulent gas dynamics, creating a more stable if less vibrant environment. The merger represents the local culmination of cosmic structure formation. Large galaxies form through hierarchical assembly, smaller systems merge to build increasingly larger ones, and the Milky Way Andromeda collision exemplifies this process. After merger, Milkomeda will be the dominant galaxy in the local group by a substantial margin, possibly accreting remaining dwarf galaxies over subsequent billions of years. Eventually, perhaps 100 billion years in the future, it may be the only visible galaxy as cosmic expansion carries all other groups beyond the cosmic event horizon. Observing similar mergers in distant galaxies allows astronomers to preview our local future. Systems like the Antennae galaxies, the Mice galaxies, and ARP 220 show various merger stages from initial encounter through final coalescence. These observations reveal common features: extended tidal tails of stars, intense central starbursts, and the gradual dissolution of spiral structure into amorphous elliptical forms. Each observed merger refines simulations of the Milky Way Andromeda collision, improving predictions of specific outcomes and timescales. The merger will also affect the broader local group. The Triangulum galaxy, M33, currently orbiting Andromeda at roughly 750,000 light-years distance, faces an uncertain fate. Some simulations suggest it will merge with Andromeda before the Milky Way collision, adding its 40 billion stars to the mix. Other scenarios place it on a trajectory that allows it to survive the initial merger, only to be accreted later. Smaller dwarf galaxies will be scattered, tidally disrupted, or absorbed, ultimately joining Milkomeda's extended stellar halo. Andromeda's magnetic field structure. Permeating Andromeda's disk and halo is an extensive magnetic field, invisible to optical telescopes, but detectable through its effects on radio wave propagation and particle dynamics. This field, Though extraordinarily weak by terrestrial standards, roughly 1 million times weaker than Earth's surface magnetic field, plays crucial roles in regulating star formation, guiding cosmic ray propagation, and shaping large-scale galactic structure. Understanding Andromeda's magnetic field provides insights into dynamo processes that generate and sustain fields throughout spiral galaxies. Radio observations reveal the field structure through synchrotron emission radiation produced by electrons spiraling through magnetic fields at relativistic speeds. These cosmic ray electrons, accelerated by supernova shocks and other energetic processes, emit radio waves whose intensity and polarization depend on magnetic field strength and orientation. Maps of polarized radio emission show that Andromeda's field follows a spiral pattern broadly aligned with the stellar and gaseous spiral arms, with field strengths typically ranging from 5 to 10 microgauss in the disk. The spiral field pattern suggests an ordered, large-scale structure rather than random turbulent fields. Such ordered fields arise through galactic dynamo processes, the conversion of kinetic energy from galactic rotation and turbulent gas motions into magnetic energy. Differential rotation, where inner regions orbit faster than outer regions, stretches and amplifies initial seed fields, wrapping them into spiral configurations over hundreds of millions of years. Turbulence from supernova-driven convection provides the small-scale stirring that completes the dynamo cycle. Field strength varies systematically with radius. Maximum strength occurs in the star-forming ring between 30,000 and 50,000 light-years from the center, where gas density and star formation rate both peak. In these regions, fields reach 10 to 15 microgauss, strong enough to provide substantial pressure support against gravitational collapse and to significantly affect gas dynamics. Weaker fields of 2 to 5 microgauss characterize the outer disk where gas density and star formation decline. The field orientation alternates between pointing inward and outward in adjacent spiral arms, creating a bisymmetric spiral pattern. This configuration results from specific dynamo modes excited by Andromeda's rotation profile and disk structure. The alternating polarity means field lines form coherent loops, threading through the disk, similar to how field lines loop through the Sun's surface, creating solar active regions, but on scales millions of times larger. Magnetic fields provide crucial support against gravitational collapse in molecular clouds. In the absence of magnetic pressure, many more clouds would collapse to form stars, potentially exhausting gas supplies much faster than observed. The magnetic pressure effectively increases the critical mass required for collapse, regulating star formation rates and allowing galaxies to sustain formation over billions of years. This magnetic braking also removes angular momentum from collapsing clouds, solving the angular momentum problem in star formation theory. Cosmic rays, high-energy particles, including protons, electrons, and heavier nuclei, are confined by magnetic fields to the galactic disk. These particles reach energies millions to billions of times greater than their rest mass, travelling at nearly light speed. Without magnetic fields, cosmic rays would escape into intergalactic space within millions of years. Instead, magnetic scattering keeps them trapped for tens of millions of years, creating substantial cosmic ray pressure that contributes to disk stability and drives galactic winds. The vertical magnetic field structure extends the field into the halo above and below the disk. Observations detect radio emission from a thick layer several thousand light-years above the midplane, indicating magnetic fields reach this height, possibly in the form of vertical loops or a global poloidal field component threading through the disk. These vertical fields may channel hot gas from supernova-driven winds out of the disk, facilitating gas circulation between disk and halo in a galactic fountain process. Field generation requires seed fields to be amplified. These seeds might originate from magnetic fields generated in the early universe during the cosmic dark ages, or from fields created by the Biermann battery mechanism operating in the first stars and supernovae. Once even weak seed fields exist, dynamo processes amplify them exponentially over timescales of a few 100 million years until reaching equilibrium strengths where amplification balances dissipation. Andromeda's field strength approaches approximate equipartition with turbulent kinetic energy density and cosmic ray pressure, a theoretical state where magnetic, kinetic, and cosmic ray energies contribute comparable amounts to total pressure. This equipment suggests the field has reached saturation through dynamo processes, with any further amplification immediately dissipated through magnetic reconnection and wave damping. The convergence to equipartition appears universal among spiral galaxies, indicating fundamental physical principles govern field amplification. Faraday rotation measurements provide another probe of magnetic field structure. When polarized radio waves traverse magnetized plasma, the polarization plane rotates by an amount depending on electron density, magnetic field strength along the line of sight, and path length. By observing background radio sources through different parts of Andromeda's disk and halo, astronomers map the line of sight field component and electron density simultaneously, complementing synchrotron emission studies that measure the perpendicular field component. The ordered field component makes up roughly 50 to 70% of total field energy, with the remainder in random, turbulent fields at smaller scales. This relatively high degree of order indicates efficient dynamo operation and stable disk structure over long timescales. Galaxies undergoing major mergers show much more disordered fields as gravitational perturbations disrupt the regular rotation pattern needed for efficient dynamo action. Andromeda's ordered field thus reflects its current state of relative quiescence between major mergers. Magnetic fields also influence the structure of supernova remnants. The expanding shock waves from supernovae compress ambient magnetic fields, creating bright radio emission arcs. These remnants appear elongated or distorted depending on the pre-existing field geometry, with expansion proceeding more easily perpendicular to field lines than parallel. Studying remnant morphologies reveals local field structure at scales of tens of light years, complementing large-scale synchrotron maps. The field's role in galaxy evolution extends beyond current star formation. During the future collision with the Milky Way, magnetic fields will affect gas dynamics during the galaxy's interpenetration. Simulations show fields can suppress some instabilities and enhance others, altering the intensity and distribution of merger-triggered starbursts. Field amplification during compression phases may temporarily create extraordinarily strong fields of hundreds of microgauss in shocked regions. Comparing Andromeda's field to the Milky Way's reveals similarities, suggesting universal processes operate in spiral galaxies. Both show spiral patterns with comparable field strengths in star-forming regions, bisymmetric configurations, and significant ordered components. Differences appear mainly in detailed structure, slight variations in pitch, angle, arm spacing, and radial profiles reflecting each galaxy's specific formation history and current rotation profile. These comparisons validate dynamo theory predictions and constrain models of field generation mechanisms. The globular cluster system surrounding Andromeda, in a roughly spherical distribution extending over 100,000 light-years from the center, are approximately 460 confirmed globular clusters, dense, gravitationally bound systems each containing 100,000 to several million stars packed into regions just tens of light years across. These ancient stellar cities represent some of the oldest structures in the galaxy, fossils from the epoch of galaxy formation that have survived intact for over 10 billion years. Studying Andromeda's globular clusters provides insights into early galactic assembly and tests of stellar evolution in extreme environments. Globular clusters formed during Andromeda's earliest epochs, when gas clouds collapsed under their own gravity with sufficient density to avoid dispersing before stars formed. Unlike open clusters that form in galactic disks and gradually dissolve through tidal forces and stellar evaporation, globular clusters achieve high enough central densities to remain gravitationally bound for cosmic timescales. Their stellar populations are ancient and uniformly old. Most clusters show ages between 10 and 13 billion years, with relatively little age spread within individual clusters. The spatial distribution divides into distinct subpopulations. An inner population of metal-rich clusters concentrates near the galactic center, orbiting within roughly 30,000 light-years and showing flattened, disk-like distribution, suggestive of formation in or from an early galactic disk. An outer population of metal-poor clusters extends to over 100,000 light-years in a more spherical distribution characteristic of halo objects. This bimodal distribution in both space and metallicity suggests different formation mechanisms or progenitors. The inner population forming in situ within Andromeda's protodisk, the outer population potentially accreted from dwarf galaxies during mergers. The largest and brightest globular cluster in Andromeda's system, designated G1 or Male 2, contains approximately 10 million solar masses and shines with the luminosity of 1.6 million suns. Located roughly 140,000 light-years from Andromeda's center, G1 rivals the mass of some dwarf galaxies and may itself be the stripped core of a dwarf galaxy that merged with Andromeda billions of years ago. Its central density exceeds 100,000 stars per cubic light-year. In such environments, the average distance between stars is less than 1/10 of a light-year, compared to 4 light-years between the Sun and its nearest neighbour. Stellar dynamics within globular clusters create exotic phenomena impossible in less dense environments. Close gravitational encounters between stars occur regularly on timescales of millions of years, occasionally ejecting stars from the cluster entirely or forming tight binary systems. Some of these binaries contain compact objects, white dwarfs, neutron stars, or rarely black holes, accreting matter from normal stellar companions, creating X-ray sources detectable even at Andromeda's distance. Observational studies using the Hubble Space Telescope have resolved individual stars in Andromeda's globular clusters, enabling construction of color magnitude diagrams that reveal evolutionary states and ages. The main sequence turn-off point, where stars are just exhausting core hydrogen, occurs at spectral types cooler and redder than the Sun in old clusters, since lower mass stars have longer main sequence lifetimes. Measuring turn-off luminosity and comparing to stellar evolution models yields ages with uncertainties of approximately 1 billion years. The metallicity distribution shows a clear bimodal pattern, with peaks at roughly f divided by h equals -1.5 and -0.5 on the logarithmic abundance scale, where solar metallicity equals 0. This bimodality parallels that seen in the Milky Way's globular cluster system and in other large galaxies, suggesting a universal formation mechanism. The metal-poor peak likely represents clusters formed from primordial gas during the galaxy's initial collapse, while the metal-rich peak indicates formation from pre-enriched gas in the disk or accreted from gas-rich dwarf galaxies. Some clusters show spread in chemical abundances among their member stars, so-called multiple populations, indicating formation proceeded through multiple episodes of star formation, with enrichment between episodes. The first stellar generation polluted surrounding gas with products of stellar nucleosynthesis, particularly helium, nitrogen, and sodium produced in intermediate mass stars. Subsequent generations formed from this enriched material, creating the abundant spreads observed today. This discovery revolutionized understanding of cluster formation, replacing the simple picture of single-burst formation with complex, multi-phase scenarios. Dynamical evolution gradually alters cluster properties over billions of years. Two-body gravitational encounters transfer energy from core to envelope, causing central regions to contract while outer regions expand, a process called core collapse that eventually leads to very dense central concentrations. Simultaneously, stellar evolution removes mass as stars shed envelopes during red giant and asymptotic giant branch phases, causing overall cluster mass to decline. These processes cause cluster luminosity and mass to decrease gradually, with typical present-day masses representing 50 to 80% of initial formation masses. The cluster system's total mass approaches 100 million solar masses, comprising roughly 0.01% of Andromeda's total stellar mass. This specific frequency, the ratio of cluster system properties to galaxy properties, provides important constraints on formation theories. Higher specific frequencies characterize galaxies that experienced intense early star formation or major merger events, while lower values indicate quieter assembly histories. Andromeda's value falls within the normal range for large spiral galaxies. Orbital studies track cluster motions through multiple observations spanning years to decades. These motions, combined with cluster positions, allow calculation of orbits within Andromeda's gravitational potential. Orbital characteristics divide clusters into different groups. Disk clusters on roughly circular, low-inclination orbits. Halo clusters on highly elliptical orbits reaching large distances. And intermediate populations. These orbital families correspond to the metallicity and spatial distribution patterns, confirming that different cluster populations have different origins. Tidal disruption gradually removes stars from clusters through gravitational interactions with the galactic disk and bulge. Clusters passing through the disk experience strong tidal forces that strip outer members, creating tidal tails, streams of former cluster members following similar orbits. Over billions of years, this process can completely dissolve lower mass clusters, explaining why observed cluster masses show a deficit at low masses compared to theoretical predictions. Only clusters massive enough and on orbits avoiding frequent disk passages survive to the present epoch. Comparing Andromeda's cluster system to the Milky Way's reveals interesting differences. Andromeda hosts more clusters, approximately 460 versus 150 for the Milky Way, consistent with its larger stellar mass. However, the cluster-specific frequency is somewhat lower, suggesting relatively less intense early star formation or different formation efficiency. Both systems show bimodal metallicity distributions and similar age ranges, indicating similar formation epochs despite different detailed histories. The cluster system will be significantly disrupted during the future collision with the Milky Way. Close gravitational encounters between clusters from both galaxies will occasionally result in mergers or tidal disruption. Many clusters will be stripped from both parent galaxies through tidal shock during the merger, becoming intracluster objects orbiting within Milky-Meda's extended halo. A fraction will be destroyed completely, their stars scattered into the field population. Only the most massive, compact clusters will likely survive to populate the merged galaxy's globular cluster system, the stellar streams and tidal debris. Wrapped around Andromeda like ghostly ribbons are faint stellar streams, long, thin concentrations of stars tracing the orbital paths of disrupted dwarf galaxies and globular clusters. These streams represent some of the most direct evidence for galactic cannibalism, the process by which large galaxies grow by consuming smaller neighbours. Mapping Andromeda's stellar streams reveals its merger history and provides sensitive probes of the dark matter distribution that perturbs stream orbits through gravitational interactions. The most prominent stellar stream, sometimes called the giant southern stream, wraps around Andromeda's southern regions in a complex, multi-looped structure extending over 100,000 light-years. Photometric studies reveal this stream contains stars with similar ages and metallicities, indicating common origin in a single progenitor dwarf galaxy that Andromeda tidally disrupted approximately 2 to 3 billion years ago. The stream's width, just a few thousand light-years, and sharp edges demonstrate that tidal disruption was relatively recent on cosmic timescales. As older streams gradually disperse and become more diffuse through velocity dispersion and gravitational perturbations, multiple other streams have been identified through careful analysis of star counts in deep imaging surveys. Some appear as overdensities in specific regions of the halo, while others manifest as coherent structures in position-velocity space, even when spatially smeared. Each stream represents a separate accretion event, its properties encoding information about the progenitor's mass, orbit, and disruption time. The total number of detected streams approaches 24, though this represents a lower limit. Fainter streams, below current detection thresholds, almost certainly exist. Stellar streams provide exquisitely sensitive probes of Andromeda's gravitational potential. As streams orbit through the galaxy, their trajectories depend precisely on the underlying mass distribution, including both luminous matter and dark matter. Small deviations in the expected smooth mass distribution, such as dark matter subhalos predicted by cold dark matter theory, create gaps, kinks, or density variations in streams. Detecting such features allows astronomers to map dark matter structure indirectly, including components too small or dark to detect through any other method. The stream morphologies reveal details about Andromeda's dark matter halo shape. If the halo is perfectly spherical, stream orbits would precess uniformly. However, observed stream configurations suggest some flattening or triaxiality in the halo, causing orbital precession rates to vary with orientation. Modeling stream dynamics while varying halo shape parameters allows inference of the true three-dimensional halo structure, providing constraints impossible to obtain from rotation curves alone, which measure only radial mass profiles. Some streams appear associated with surviving progenitor objects. In these cases, the stream traces the orbit, while the progenitor, now a stripped dwarf galaxy core, continues along the same path, gradually shedding additional stars with each passage through Andromeda's disk. Other streams lack identifiable progenitors, their parent objects completely dissolved into the stream itself. The presence or absence of surviving cores indicates how close to complete disruption the system has progressed. Stellar ages within streams vary depending on progenitor properties. Streams from dwarf galaxies that experience star formation over extended periods contain mixed-age populations, while those from ancient gas-poor dwarfs or globular clusters contain exclusively old stars. Chemical abundance patterns provide additional diagnostics. Dwarf galaxy streams show abundance ratios characteristic of their progenitors, specific star formation histories, while globular cluster streams display the unique light element abundance variations that distinguish cluster stars from field populations. The discovery rate of new streams continues accelerating as surveys reach fainter surface brightness limits. Modern digital surveys, combining wide-field imaging with careful photometric calibration and sophisticated data analysis techniques, reveal structures at surface brightnesses below 30 magnitudes per square arc second over, 1,000 times fainter than the dark night sky. At these depths, Andromeda's entire halo reveals itself as a complex web of streams, shells, and overdensities representing the accumulated debris from billions of years of accretion. Kinematic studies using spectroscopy measure radial velocities of stars in streams, providing the third dimension of phase space information. Combining positions and velocities allows reconstruction of orbital history, where the progenitor originated, when disruption began, how many orbits have elapsed since. These reconstructions sometimes reveal surprising results, such as progenitors arriving from unexpected directions or disruption occurring more recently than morphology alone suggests. The stream populations will be dramatically affected by the approaching collision with the Milky Way. Gravitational perturbations during the merger will scatter stream stars, destroying coherent structures and mixing stars from different streams together. New streams will form from the merger itself as tidal forces extract stars from both galaxies' outer regions. The resulting merged galaxy's halo will contain a complex mixture of old streams from each progenitor galaxy plus new merger-generated streams, creating an extraordinarily complicated fossil record requiring sophisticated analysis to disentangle. Comparing Andromeda's streams to those around the Milky Way reveals both similarities and differences. The Sagittarius stream in the Milky Way closely parallels Andromeda's giant southern stream in structure and origin, suggesting similar disruption processes operate in both systems. However, Andromeda appears to have more prominent streams overall, possibly indicating a more recent major accretion event or simply reflecting observational advantages. External galaxies allow simultaneous viewing of the entire halo, while Milky Way streams require all-sky surveys and distance determinations to map fully. Theoretical simulations predict that all large galaxies should possess extensive stream networks from hierarchical assembly, and observations of Andromeda strongly confirm these predictions. The streams demonstrate that galaxy growth through mergers is not merely theoretical, but an ongoing process observable in nearby systems. Each stream represents a smaller galaxy's final chapter. Its independent existence ended, but its stellar population permanently incorporated into a larger structure, continuing to orbit long after the parent object's gravitational identity disappeared. Andromeda in the cosmic web. Andromeda does not exist in isolation, but occupies a specific location within the cosmic web, the large-scale structure of matter that networks the universe with filaments, walls, and voids spanning hundreds of millions of light-years. Understanding Andromeda's position within this structure provides context for its formation, evolution, and relationship to the broader universe. The galaxy resides within a relatively modest filament, connecting the local group to larger superclusters, influencing its gas supply, merger history, and long-term fate. The local group, dominated by Andromeda and the Milky Way, occupies a filament stretching between the Virgo supercluster, roughly 50 million light-years distant, and other structures in the opposite direction. This filament channels matter flow on the largest scales, with gas and small galaxies streaming along the filament toward denser concentrations. Andromeda's position within the filament, rather than in an isolated void region, has likely enhanced its mass growth by providing continuous, if sparse, accretion of gas from the intergalactic medium. The filament structure emerged from initial density fluctuations in the early universe, amplified over billions of years through gravitational instability. Regions of slight overdensity attracted more matter, growing into filaments and nodes where filaments intersect. Underdense regions became voids, expanding faster than the cosmic average and pushing matter toward filament boundaries. This process created the foam-like structure observed in large-scale galaxy surveys, with galaxies concentrated in filaments and sheets surrounding vast empty voids. Andromeda's motion relative to the cosmic microwave background, the reference frame defined by the Big Bang's afterglow, reveals the local group's motion through the cosmic web at approximately 630 kilometers per second, toward a region dubbed the Great Attractor in the constellation Hydra Centaurus. This motion reflects the gravitational pull of overdense regions along our filament and in the broader supercluster structure, demonstrating that even massive galaxies remain subject to larger-scale gravitational flows. The web's structure influences gas accretion onto galaxies. Cold gas flows along filaments toward nodes and galaxies within them, potentially providing continuous fuel for star formation. This cold mode accretion delivers gas at temperatures around 10,000 Kelvin directly to galaxy disks, without shock heating to millions of degrees. Evidence for such flows remains indirect and debated, but theoretical models suggest they play important roles in sustaining star formation in massive galaxies like Andromeda over cosmic time. Andromeda's satellite galaxy distribution may reflect the filamentary structure on smaller scales. The observed planar distribution of satellites could trace a filament or sheet of matter that preferentially feeds material to Andromeda from specific directions. If confirmed, this would link galaxy-scale structure to cosmic web structure, demonstrating that large-scale patterns propagate downward in scale through gravitational dynamics. The local group's position between Virgo and more distant structures places it in a relatively quiet region compared to rich galaxy clusters. Cluster environments exhibit much higher galaxy densities, frequent interactions, and environmental effects like ram pressure stripping that remove gas from galaxies. The local group's more isolated position has allowed Andromeda to retain gas and continue star formation, whereas similar galaxies in cluster cores often become red and dead ellipticals, stripped of star-forming material. Future evolution will gradually incorporate the local group more firmly into larger structures. As cosmic time progresses and structures grow through gravitational aggregation, the local group may eventually merge with the Virgo cluster or other nearby concentrations. However, the accelerating cosmic expansion driven by dark energy will likely prevent this expansion, carries distant structures away faster than gravity can draw them together, effectively freezing the large-scale structure and leaving the local group permanently isolated from most other galaxy groups. The web structure visible today represents matter distribution at the present epoch, but its evolution traces back to the cosmic dark ages just after the Big Bang. Initial quantum fluctuations during cosmic inflation seeded slightly denser and less dense regions in the primordial plasma. After recombination, when matter and radiation decoupled, gravity amplified these fluctuations, drawing matter into progressively denser concentrations that eventually formed the first stars, galaxies, and the filamentary web connecting them. Andromeda's position provides observational advantages for cosmological studies. As an external galaxy relatively nearby, it allows detailed examination of processes that cosmological observations detect only statistically in averaged samples of distant galaxies. Studying Andromeda's gas content, star formation, and structure provides ground truth for interpreting observations of similar galaxies at high redshift when the universe was younger and galaxies were still actively assembling. The cosmic web will gradually dissolve on the longest timescales as dark energy's influence grows. Currently, structures within a few tens of millions of light years remain gravitationally bound, resisting cosmic expansion. But as expansion accelerates, this bound scale shrinks. Eventually, only the local group and its immediate environs, whatever remains after the Milky Way-Andromeda merger, will remain gravitationally connected, surrounded by an exponentially expanding void as all other structures recede beyond the cosmic event horizon. The future of Andromeda. Andromeda's future unfolds along trajectories determined by known physical processes and observable current conditions, allowing astronomers to project its evolution across billions of years with reasonable confidence. The dominant event shaping this future is the inevitable collision with the Milky Way, but other processes, stellar evolution, gas depletion, satellite accretion, and cosmological expansion, will also contribute to transforming the galaxy from its present state into something unrecognizable. Over the next 2 billion years, before collision effects become dominant, Andromeda will continue evolving gradually through secular processes. Star formation will persist in spiral arms at declining rates as gas supplies diminish through conversion to stars and possible ejection through galactic winds. The total gas mass will decrease from the current several billion solar masses to perhaps half that value, reducing star formation rates proportionally. The galaxy's overall color will redden slightly as massive blue stars evolve away while lower mass red stars accumulate. Satellite galaxy accretion will continue, adding mass gradually to Andromeda's halo. Current satellites like M32 and M110 will spiral slowly inward through dynamical friction, with M32 potentially merging within 2 to 3 billion years given its close proximity. Each merger adds stars to the halo and may trigger localized starbursts if the accreted satellite retained gas. These minor mergers won't dramatically alter Andromeda's overall structure, but will incrementally increase total mass and extend the stellar halo. As the collision with the Milky Way approaches, tidal effects will become increasingly significant. Beginning perhaps 1 billion years before first close passage, gravitational interactions will start distorting both galaxies' outer structures. Stars in the outermost regions will feel differential gravitational forces stronger pull toward the approaching galaxy than inner regions experience, creating tidal bulges that elongate both systems along the collision axis. These distortions will gradually intensify until becoming visually obvious several 100 million years before impact. The collision itself will unfold over approximately 2 to 3 billion years through multiple close passages as the galaxies orbit their common center of mass while losing energy to tidal friction. Each passage strips material into tidal tails, compresses gas clouds triggering starbursts, and perturbs stellar orbits. Computer simulations show the stellar components will gradually merge into a single elliptical system, while gas dynamics produce intense but short-lived star formation, consuming most remaining gas within a few 100 million years of final coalescence. The resulting merged galaxy, Milkomeda, will differ fundamentally from both progenitors. The elegant spiral structure will be completely destroyed, replaced by a smooth, elliptical or spheroidal morphology with little organized rotation. Stars will orbit in randomized directions rather than coherent circular paths, creating the characteristic appearance of elliptical galaxies' smooth, featureless light distributions declining gradually with radius. The merger will effectively end the era of spiral galaxy dynamics, creating an entirely new dynamical system. Star formation in Milkomeda will decline precipitously after the merger-driven starburst exhausts accessible gas. Any remaining gas will be primarily hot and diffuse, unable to cool and collapse into new stars. The galaxy will enter a red and dead state, dominated by old, cool stars, red giants, red dwarfs, and dying intermediate mass stars. Over subsequent billions of years, even these stars will evolve away, replaced by stellar remnants, white dwarfs, neutron stars, and black holes. Milkymeda's luminosity will decline steadily as fewer active stars remain to emit light. The merged supermassive black hole at Milkymeda's center will settle into quiescence after consuming merger-shocked gas. With minimal remaining gas supply, accretion rates will drop to negligible levels, and the black hole will become essentially invisible except through its gravitational effects. Occasionally, a star will pass close enough to be tidally disrupted, providing brief bursts of activity as stellar debris spirals into the black hole, but such events will be rare, perhaps 1 per 10,000 to 100,000 years. On timescales of 10 to 20 billion years after the merger, stellar evolution will dramatically alter Milkymeda's appearance. The longest-lived stars, red dwarfs with masses below zero, 5 solar masses will continue burning hydrogen for trillions of years, but all more massive stars will have completed their evolution. This means stars like the Sun will have exhausted their fuel and become white dwarfs. Even intermediate mass red giants will have disappeared, leaving a population dominated by the faintest red dwarfs and stellar remnants. The galaxy's luminosity will have declined by perhaps 90% from peak. Cosmological expansion will increasingly isolate Milkymeda from other structures. Due to accelerating expansion driven by dark energy, galaxies currently visible will gradually recede beyond the cosmic event horizon, the distance beyond which light can never reach us, regardless of how long we wait. Within approximately 100 to 150 billion years, only galaxies currently in the local group will remain visible. All else will have redshifted into invisibility, leaving Milkymeda in an apparently empty universe surrounded by darkness in all directions. The faint remaining dwarf galaxies in the local group will eventually merge with Milkymeda as well, their orbits decaying through dynamical friction until they coalesce with the central system. By perhaps 50 billion years after the Milky Way Andromeda merger, all local group galaxies will have joined into a single structure, a large elliptical galaxy containing all the stars from dozens of formerly independent systems, orbiting in a vast extended halo around the merged core. Beyond 100 billion years, Milkymeda enters the era of stellar death. Main sequence star formation ceased billions of years earlier when gas supplies were exhausted. Now, even the longest-lived stars besides the smallest red dwarfs begin dying. The galaxy becomes a collection of stellar corpses, perhaps 100 billion white dwarfs, tens of millions of neutron stars, millions of stellar mass black holes, and one central supermassive black hole containing hundreds of millions of solar masses. The only remaining active stars are the ultra-low mass red dwarfs, glowing feebly and doomed to burn for trillions of years more. The final stages of Milkymeda's evolution extend across timescales that dwarf the current age of the universe. Even red dwarfs eventually exhaust their hydrogen after 10 trillion years, becoming white dwarfs and adding to the stellar graveyard. White dwarfs cool gradually, taking quadrillions of years to radiate away their thermal energy and become black dwarfs, cold, inert spheres of degenerate matter invisible in any wavelength. The galaxy becomes a dark, cold collection of remnants orbiting the central black hole. On even longer timescales approaching 100 years, black holes themselves evaporate through Hawking radiation quantum effects, causing them to emit particles and gradually lose mass. The smallest black holes evaporate first, followed by progressively larger ones, with the supermassive central black hole persisting longest. Eventually, it too will evaporate, its mass converted to radiation dissipating into the exponentially expanding void. What began as a magnificent spiral galaxy containing 1 trillion stars ends as scattered radiation in an empty, dark universe. The X-ray and high-energy emissions. Beyond visible light, Andromeda reveals a hidden universe of violent processes observable only through X-ray and gamma-ray observations. Space-based observatories like Chandra, XMM Newton, and NuStar have mapped thousands of discrete X-ray sources throughout the galaxy, each representing extreme physical environments, supernova remnants, accreting black holes, neutron stars, and hot diffuse plasma heated to millions of degrees. These high-energy emissions provide unique insights into stellar death, compact object populations, and the energetic processes shaping galactic evolution that remain invisible to optical telescopes. The X-ray source population divides into distinct categories based on luminosity and spectral characteristics. Low-mass X-ray binaries contain neutron stars or black holes accreting matter from companion stars typically less massive than the Sun. Matter spirals through an accretion disk, heating through friction to temperatures exceeding 10 million Kelvin before reaching the compact object's surface or event horizon. These systems emit predominantly soft X-rays with energies around 0.5 to 2 keV. Andromeda hosts approximately 1,200 detected low-mass X-ray binaries, though the true population likely exceeds several thousand when accounting for systems below detection thresholds. High-mass X-ray binaries feature massive stellar companions, O or B spectral types, exceeding 10 solar masses, whose powerful stellar winds feed compact object accretors. These systems produce harder X-ray spectra extending to energies above 10 keV and exhibit more variable emission patterns, reflecting wind structure variations and orbital modulation. The high-mass binary population concentrates in star-forming regions within spiral arms, reflecting their short-lived massive progenitors that explode as supernovae just millions of years after formation. Approximately 200 high-mass X-ray binaries have been identified in Andromeda's disk. Supernova remnants generate extended X-ray emission from shock-heated gas expanding at thousands of kilometers per second. When the supernova blast wave encounters ambient interstellar material, it compresses and heats the gas to temperatures approaching 10 million Kelvin, producing thermal X-ray emission characteristic of specific elements, oxygen, neon, magnesium, silicon, and iron, synthesized during stellar nucleosynthesis and explosive burning. Chandra's angular resolution resolves individual remnants as rings or shells of emission, with diameters ranging from a few light-years for young remnants to over 100 light-years for older ones. Approximately 50 supernova remnants have been catalogued in Andromeda, though hundreds likely exist below detection limits. The central region harbours the most luminous X-ray source emission associated with the supermassive black hole, though at relatively low luminosity compared to active galactic nuclei in other galaxies. The accretion rate onto Andromeda's 110 to 230 million solar mass black hole appears quite low, producing X-ray luminosity around 1036 ergs per second, roughly 100 times the Sun's total luminosity, but millions of times below quasar luminosities. This quiescence suggests the black hole has exhausted easily accessible fuel in its immediate vicinity, occasionally flickering brighter when gas clouds wander too close. Diffuse hot gas permeates Andromeda's halo, producing faint extended X-ray emission detectable only through long integration exposures combining many observations. This plasma, heated to temperatures around 1 to 3 million Kelvin, likely originates from supernova-driven galactic fountains and ancient merger events. The gas fills a volume extending at least 50,000 light-years from the galactic plane, forming a tenuous corona analogous to, but less massive than the Milky Way's hot halo. Total gas mass in this component approaches 100 million solar masses, representing material expelled from the disk, but retained by Andromeda's gravitational potential. Ultra-luminous X-ray sources, objects with luminosities exceeding 1039 ergs per second, constitute a mysterious population detected throughout Andromeda. These systems radiate at luminosities that appear to require black holes exceeding 10 solar masses accreting at near maximum rates, or possibly intermediate mass black holes containing hundreds of solar masses. Approximately 40 ultraluminous sources populate Andromeda's disk and bulge, preferentially concentrated in star-forming regions. Their nature remains debated. Some may be stellar mass black holes with beamed emission making them appear brighter than isotropic emission would produce, while others might genuinely contain intermediate mass black holes formed through exotic channels. X-ray binaries serve as probes of compact object populations, the census of neutron stars, and stellar mass black holes produced by past supernova explosions. Each detected X-ray binary represents an accreting compact object, but many more compact objects exist in isolation or in binaries not actively accreting. Statistical arguments suggest that for every accreting system, perhaps 1,000 compact objects remain dark and undetectable. Andromeda's compact object population thus likely exceeds several million neutron stars and hundreds of thousands of stellar mass black holes distributed throughout the bulge, disk, and halo. Spectroscopic analysis of X-ray emission reveals detailed physics of accreting systems. Iron K-alpha emission lines at 6.4 keV appear broadened and skewed by relativistic effects near black holes, gravitational redshift, and Doppler shifts from material orbiting at substantial fractions of light speed. These line profiles allow measurement of black hole spin and confirmation of general relativistic predictions in strong field regimes. Similar analyses applied to Andromeda's brightest X-ray binaries test whether black holes in external galaxies exhibit properties matching those in the Milky Way. Timing analysis reveals periodic variations corresponding to orbital periods, neutron star rotations, and quasi-periodic oscillations reflecting instabilities in accretion disks. Pulsating X-ray sources with periods from milliseconds to seconds identify rotating neutron stars whose magnetic fields channel accreting material to polar caps, creating lighthouse-like beamed emission. These pulsars provide independent mass measurements through analysis of pulse timing variations, constraining neutron star equations of state, the relationship between pressure and density in nuclear density matter that determines whether matter can support neutron star masses above certain limits or collapse to black holes. Gamma-ray observations from Fermi-LAT detect emission from Andromeda at energies exceeding 100 MeV, though at low significance, requiring careful analysis to separate from background. The detected emission likely originates from cosmic ray interactions with interstellar gas and radiation fields, producing pion decay gamma rays and inverse Compton scattered photons. The gamma-ray luminosity correlates with star formation rate and gas content, as expected if cosmic rays produced by supernovae diffuse through the interstellar medium, producing gamma rays through these processes. This emission provides complementary information about cosmic ray populations not accessible through other observations. Future X-ray missions with improved sensitivity and angular resolution will dramatically expand understanding of Andromeda's high-energy universe. Missions like Athena, planned for launch in the 2030, will detect thousands more X-ray sources, resolve spectral features with unprecedented energy resolution, and map diffuse emission structures in detail. These observations will constrain compact object populations, measure feedback from stellar evolution on the interstellar medium, and trace hot gas flows between disk and halo, connecting stellar processes to large-scale galaxy evolution through the high-energy signatures they produce across cosmic time. Chemical abundances and nucleosynthesis. Andromeda's chemical composition tells the story of 13 billion years of stellar alchemy, the gradual transformation of primordial hydrogen and helium into the full periodic table of elements through nuclear fusion in stellar cores, and explosive nucleosynthesis in supernovae. Measuring chemical abundances throughout the galaxy reveals how elements form, how they disperse through interstellar space, and how metallicity evolved from the metal-poor early epochs to the metal-rich present. This chemical archaeology provides crucial constraints on star formation history, stellar yields, and galactic evolution that complement purely dynamical and photometric studies. The primordial composition inherited from the Big Bang consisted of roughly 75% hydrogen, 25% helium by mass, and trace lithium. All heavier elements, collectively termed metals in astronomical parlance, regardless of chemical properties formed in stars after the first stellar generations ignited. Each element traces specific nucleosynthetic channels: carbon and oxygen from intermediate mass stars, iron from type Ia supernovae, alpha elements like magnesium and silicon from core collapse supernovae, and neutron capture elements like europium and gold from neutron star mergers or rare supernovae. Spectroscopic observations of individual stars in Andromeda measure chemical abundances through analysis of absorption lines in stellar spectra. Each element produces characteristic absorption features at specific wavelengths when light from the stellar photosphere passes through cooler atmospheric layers. Line strength depends on element abundance, temperature, pressure, and ionization state, requiring sophisticated model atmosphere calculations to extract accurate abundances. Despite Andromeda's 2.5 million light-year distance making individual star spectroscopy challenging, modern 8 to 10 meter class telescopes with efficient spectrographs resolve bright giants and supergiants, yielding metallicities and abundance patterns comparable in quality to Milky Way studies. The overall metallicity gradient shows systematic decline from center to outer regions. The bulge exhibits metallicities ranging from solar values to twice solar, indicating intense early star formation that rapidly enriched the interstellar medium. At intermediate radii, around 30,000 to 50,000 light-years, metallicities drop to roughly solar values, while outer disk regions beyond 80,000 light-years show metallicities 0.3 to 0.5 times solar. This gradient quantifies inside-out formation, with inner regions reaching high metallicities early when star formation rates peaked, and outer regions accumulating enrichment more gradually from sustained lower rate formation. Alpha element abundances oxygen, magnesium, silicon, sulfur, calcium, and titanium provide chemical clocks indicating formation timescales. These elements form predominantly in massive stars that explode as Type II supernovae within tens of millions of years after formation. Iron, conversely, comes primarily from Type Ia supernovae, involving white dwarf explosions that require hundreds of millions to billions of years to occur after initial star formation. The alpha to iron ratio thus distinguishes rapid star formation episodes that ended before Type Ia supernovae contributed substantially versus extended formation, allowing iron enrichment to accumulate. Andromeda's bulge shows enhanced alpha to iron ratios around alpha divided by phi equals plus 0.3 dex, indicating formation occurred rapidly, probably within 1 to 2 billion years before significant Type Ia supernova iron production. The disk shows progressively lower alpha to iron ratios approaching solar values, consistent with extended star formation over 8 to 10 billion years, allowing both nucleosynthetic channels to reach equilibrium. These patterns parallel those in the Milky Way, suggesting similar formation timescales for bulges versus disks, despite differences in total mass and merger histories. Neutron capture elements produced through slow S process and rapid process. Neutron capture nucleosynthesis reveal additional formation details. The S process operates in asymptotic giant branch stars that dredge newly synthesized elements to their surfaces through convection, then disperse them through stellar winds. Elements like barium, lanthanum, and cerium trace S process contributions. The R process requires extraordinarily neutron-rich environments, likely neutron star mergers or rare magneto-rotational supernovae, producing elements like europium, gadolinium, and thorium. The R process to S process abundance ratio indicates the relative contribution of these channels. Metal-poor stars in Andromeda's halo, those with Fe H below -2, show pure R process patterns with enhanced europium relative to barium, indicating formation before significant S process contributions from evolved intermediate mass stars. These ancient stars preserve the nucleosynthetic signatures of the galaxy's earliest epochs, when rapid star formation in protogalactic fragments produced numerous core collapse supernovae and possible neutron star mergers, but insufficient time had elapsed for S process enrichment. Each metal-poor star's abundance pattern potentially identifies its birth environment, whether in Andromeda's proto-halo or in a subsequently accreted dwarf galaxy. Carbon and nitrogen abundances trace mixing and dredge-up processes in evolved stars. Carbon production occurs through helium burning via the triple alpha process, while nitrogen forms through CNO cycle hydrogen burning. Stars reaching the asymptotic giant branch phase dredge carbon from helium-burning shells to surfaces through thermal pulses, becoming carbon stars with C-O ratios exceeding unity. Some stars show enhanced nitrogen from CNO process material mixed to surfaces during earlier red giant branch evolution. These abundances constrain stellar evolution models and the contribution of low versus high mass stars to galactic chemical enrichment. Oxygen, the third most abundant element after hydrogen and helium, serves as a fundamental metallicity indicator. Oxygen lines appear prominently in stellar spectra and HII region emission spectra, allowing abundance measurements across multiple stellar populations and ionized gas regions. Oxygen forms almost exclusively in massive stars through helium and carbon burning, followed by supernova explosion, making it a relatively straightforward tracer of massive star enrichment, uncontaminated by Type Ia supernova contributions that dominate iron production. Emission nebulae throughout Andromeda's star-forming regions provide gas phase abundance measurements complementing stellar abundance studies. Spectroscopy of HII regions measures emission line ratios that depend on temperature, density, and elemental abundances. Oxygen, nitrogen, sulfur, and other elements produce optical emission lines whose intensities relative to hydrogen emission directly indicate gas phase abundances at locations of current star formation. These measurements reveal the present-day metallicity of star-forming gas, representing the cumulative enrichment from all previous stellar generations. Abundance gradients in the gas phase match those in stellar populations, confirming that stellar measurements represent the composition at formation rather than subsequent evolution modifying surface abundances. The radial oxygen gradient in Andromeda shows decline of approximately 0.02 to 0.03 dex per kiloparsec, similar to gradients in other spiral galaxies. This consistency suggests universal mechanisms inside-out formation combined with radial gas flows and stellar migration establish metallicity gradients regardless of specific galactic properties. Comparing chemical abundances between Andromeda and the Milky Way reveals remarkable similarities despite different masses and detailed histories. Both show similar bulge and halo metallicity distributions, similar disk abundance gradients, and similar alpha enhancement patterns in old populations. These parallels indicate that fundamental physical processes governing star formation, stellar evolution, and chemical enrichment operate universally across spiral galaxies, producing convergent outcomes even when formation details differ. The chemical composition thus encodes both universal processes and galaxy-specific history, requiring careful analysis to separate these components and extract maximum information about galactic evolution.